Okay, so now we're going to talk about what to do when you have some definite integrals happening in your problems. So when using U substitution with a definite integral, it is often convenient to determine the limits of integration for the variable u rather than to convert the antiderivative back to the variable x and evaluate it at the original limits. This change of variables is stated explicitly in the next theorem. So if a function u equals g of x has a continuous derivative on the closed interval a to b, and f is continuous on the range of g, then the definite integral from a to b of f of g of x times g prime d of x equals the definite integral from g of a to g of b of f of u du. Now, I know that was complicated and you probably didn't understand it, but when we do one, you'll see it's not so bad. So let's do one right now. Let's evaluate the definite integral from 0 to 1 of x times the quantity x squared plus 1 cubed dx. This is screaming using substitution because you have a function to a power times something that's close to the derivative of the inside. So if I let u equal x squared plus 1, then du equals 2x dx, which means that du over 2 equals x dx. Now here's the thing. Remember I said you have to substitute everything, all the x's in differentials dx. So I would do that. But notice this problem is in terms of x. So the limits are as x goes from 0 to 1. But now we're changing the variable to be in terms of u. So when x is 0, if u is x squared plus 1, if x is 0, u is 0 squared plus 1, or 1. When x is 1, that's the upper limit. That's where I'm getting these 0 and 1s. Plug that in for the equation that relates u and x. Be 1 squared plus 1, or 2. So the integral becomes 0 to 1 are the original limits. So the integral becomes 1/2 integral from 1 to 2 of u cubed. So the u replaces the x squared plus 1. The 1/2 du replaces the x dx. And the 0 and 1 are replaced by 1 and 2 because those are the limits in terms of u. Now I anti-differentiate and I get u to the 4th over 4 times 1/2, which would be u to the 4th over 8. But notice I don't have to back substitute to get this in terms of x anymore because I created an equivalent integral in terms of u. I changed the limits to be in terms of u. So now I can just plug in 2 and 1 and subtract. If I plug in 2, I'll get 4. This would be 16 over 4. And if I plug in 1, I would just get 1 over 4, which simplifies to 15 over 8. All right, so try rewriting the antiderivative in terms of the variable x and evaluate the definite integral at the original limits of integration. So here's what I'm saying with this. You can do the change of variables of definite integrals in 2 ways. You can get everything in terms of u, change the limits to be in terms of u, and then just evaluate your antiderivative at the u step. Or you can leave the limits in terms of x, but after you take the antiderivative, back substitute to get the antiderivative in terms of x, then plug in your limits for what they were in terms of x. Okay? You should get the same answer no matter which way you do it, but sometimes it's a lot easier to get your integral in terms of u and your limits in terms of u. You see right here, it was just u to the 4th, plug in 2 and 1 and subtract. Here it was x squared plus 1 to the 4th over 4, plug in 1 and 0, and subtract. So you kind of get a feel for them, and you should get the same result no matter which way you do it. So if you are able to use pattern recognition to find the antiderivative, then you do not need to change the limits of integration. So the steps for 7 would be just notice that you multiply and divide by 2, and then apply the general power rule, and then you get 15/8. But I did it with this one. We did it with this one so that we have a relatively simple example with not too many bells and whistles in it to see how you could do it either way. So remember, if you leave it in terms of u, you have to change the limits to be in terms of u. If you back substitute and get it in terms of x, use the original limits, and you don't have to solve the limits to be in terms of u. All right, let's do this one. A equals the integral from 1 to 5 of x over 2x minus 1, square root of 2x minus 1. So to evaluate this integral, let u equal 2x minus 1. Then you obtain u squared equals 2x minus 1. And u squared plus 1 equals 2x. And x equals u squared plus 1 over 2. So you might be saying, okay, up to this point, everything that u was always the inside. How come we made this the square root and not just the 2x minus 1? Well, let me show you. If you let u equal 2x minus 1, then du equals 2dx. Looking good so far, I can just divide off. And then the x equals u plus 1 over 2. So this would end up being integral x times 2x minus 1 to the negative 1/2. And x is u plus 1 over 2. Put my integral symbol in there. U to the negative 1/2. And you'd have du, and then a half out there. You could do it that way as well. That would be fine. Okay, we're just doing it a different way this time. Maybe I'll go back and finish it that way after we do it this way. So if I let u equal the square root of 2x minus 1, I square both sides, then solve for x, and I get x equals u squared plus 1 over 2. So if I differentiate each side back here, du equals dx. Before substituting, determine the new upper and lower limits of integration. When x is 1, u is square root of 2 minus 1, or 1. When x is 5, u is the square root of 10 minus 1, or 3. So this integral becomes the integral from 1 to 3 of 1 over u times u squared plus 1 over 2 times u. Notice this u and the 1 over u will simplify. And then you just have, you can factor the 1/2 out. Then you just have the integral from 1 to 3 of u squared plus 1. Anti-differentiate. Don't forget to multiply by your factor of half there. Plug in 3 and 1 and subtract. And you get 16/3. Okay? So geometrically, you can interpret the equation that the integral in terms of x equals the integral in terms of u to mean that the two different regions that represent these definite integrals represent the area of have the same area. So this is the first one in terms of x. This is the second one in terms of u. Now notice this one's wider, but doesn't go quite as high. This one's higher, but doesn't go quite as wide. And it turns out that they have the same area because it's essentially the same type of problem. All right? So let me go back because I wanted to do this integral with u equals 2x minus 1. So we're going to have it as x times 2x minus 1 to the negative 1/2 power. U equals 2x minus 1. Du equals, it would equal 2 dx, so I'm just going to divide by 2 right here and get dx. And x is going to equal u plus 1 over 2. So add 1, divide by 2. So if I do u of 1, in other words, I'm substituting when x is 1, what's u going to end up being? When x is 1, u is going to end up being 1. And when x is 5, you would have 10 minus 1, which is 9. So you're going to get the definite 1/2, the definite integral from 1 to 9. The x gets substituted with the u plus 1 over 2. And the 2x minus 1 gets substituted with u, so it'd be times u to the 1/2. And the dx gets substituted with du over 2. I already put the 1/2 out here, so it's just going to be du. So that'd be 1/4. I'm going to divide out or factor out this 1/2. And then the u to the 1/2 is going to distribute to both of those. So the integral of u to the 3/2 plus u to the 1/2 du. So you end up with 1/4 u to the 5/2 2/5 plus u to the 3/2 2/3 from 1 to 9. So what do we get? You get 1/4 times, well, if I plug in 9, oh, this is going to get super complicated. That's probably why they did it as the square root. So if you plug in 9, you would do 9 to the 5/2 power, which is like square rooting it and taking it to the 5th power. So that would be 9. Square root of 9 is 3. 3 to the 5th power. Oops. 3 to the 5th power is 243. So you'd have 2/5 times 243 plus 2/3 times, so if I plug in 9, square root it, I get 3. 3 cubed is 27. So that's that first one. Minus, if I plug in 1, I would get 2/5 plus 2/3. So let's see, 1/4 times 2/5 times 243 plus 2/3 times 27. Is that parentheses? That one. Minus 2/5 plus 2/3. And you would get, should get the same answer of 16/3. All right, cool. So we talked about that. So when evaluating definite integrals by substitution, it's possible for the upper limit of integration of the u variable form to be smaller than the lower limit. If this happens, don't flip it over and take the opposite. Don't rearrange the limits. Simply evaluate as usual. For example, after substituting u equals square root 1 minus x in this integral, if u is square root 1 minus x and you plug in 0 and 1, the upper limit becomes 0 and the lower limit becomes 1. You get this substitution. Okay, and the lower limit becomes 1 and the upper limit becomes 0. Just leave it like that, and then you could evaluate as normal. All right, well, that was it. One more video.